I'm Frank Slazer. I'm the president and CEO of the Coalition for Deep Space Exploration. We're pleased to host this series that we're calling Space 101. And Space 101 is it's really kind of an opportunity for people in the communications world and the media world to get some of the background behind space exploration, how it's done, really the science behind it, the technology behind it, and also what do we do once we get into space, and then particularly what's going to be possible in the next decade or so as we get new capabilities online. And so we thought we'd have a session today talking about how the Artemis I mission, which is going to be happening probably in the May-June timeframe, will actually enable science right from the very start. That test flight is going to contain some science. Kimberly will share some of that. There were some exciting proposals, including interstellar probes. Ralph's going to talk a little bit about that. And then Heidi's with AURA, Association of University Research Astronomy. I'm remembering. Pretty close. Okay. We'll talk a little bit about an organization that's been very involved with space telescopes and astronomy for decades, and is looking to the future and what we can do as follow-ons to the James Webb Space Telescope. And if you think it's too soon to start thinking about that, just remember James Webb, actually Hubble started back in probably like the 60s, and James Webb started probably in the early 90s, late 80s, and these things take a long time to define and develop. And so identifying the capabilities you're going to be able to launch them with is a big part of it. It helps you plan your mission out, and hopefully reduces your technology risk, so you don't have all this like elaborate origami thing to fold up and that sort of thing. So we'll talk a little bit about all those things today. Our moderator is Mary Angola, who is here from Aerojet Rocketdyne's communications organization. And I guess I'll turn it over to Mary. She's going to do a moderated discussion. We might have a few charts or videos, little things like that along the way, but basically it's going to be about 30 minutes of presentation, maybe a little bit longer. And then there'll be time for folks on the line to ask questions in real time for the presenters. And then I'll close up towards the end. But Mary, take it away.
All right. Thank you very much, Frank. And I am super excited to have Ralph and Heidi and Kimberly here today. I love science. So anybody who knows me in the office, I'm always saying, hey, let's talk about the cool science we can do. So super excited to have them. So Heidi, wanted to start with you. Hubble changed the astronomy textbooks, and we just successfully launched James Webb. So we would be remiss if we didn't talk a little bit about James Webb. So can you sort of talk to us a little bit about what we're expected to see with James Webb, and sort of what you're excited for us to see, and if you think we'll be rewriting textbooks as well?
Yeah, sure. I've been working myself personally on the James Webb Space Telescope project for over 20 years. And I got involved in this project early on because I saw the remarkable capability it would have to be transformational for science. Let me tell you a little bit, super short, what it is. It's a very large telescope, much larger than Hubble. And it's designed to be in a slightly longer wavelength of light than Hubble is sensitive to. So it is not really a successor to Hubble. It is a different kind of telescope. And it was designed with this longer wavelength of light sensitivity so that it could be sensitive to the very first galaxies that formed in the universe. That light is expanded by the expansion of our universe and shifted into the infrared. And it's really just simply beyond the ability of Hubble for that reason. And so we're really excited. But let's put up slide 28. If you could go to slide 28, perhaps, just to show a little bit of what I'm talking about. This is really talking about, if you could turn it all full screen so that just hit the play view mode. Yeah, awesome. This shows you the electromagnetic spectrum, all the light ranging from the very short wavelengths of gamma rays through the X-rays and the ultraviolet, visible, infrared, microwave, and radio. And what you can see here is that Hubble, sort of centered at the middle at visible light, is right there up in outer space. It's there. It's not there because of the absorption of the Earth's atmosphere. Our atmosphere absorbs light, and some of the light gets to the ground. That's why we have telescopes on the ground, and the optical window is one of them. And you can see here that infrared is a little bit longer, it goes to the red, but you can't, a lot of it doesn't get to the ground, pure and simple. So it doesn't matter how big your telescope is in the ground. To see some of these infrared wavelengths, you must go to outer space because of the absorption by the Earth's atmosphere. One time step will explain another reason we have to go to space. Next, could you go one slide forward? No, the other. Are we missing it? Oh, we're missing it. You took it out. Never mind. Let's see. So let me backtrack. Let's stop sharing the slides for a minute. Just go back to me. We built Hubble, we built Webb to see the very first galaxies, but that's not the only thing it can do. It can do all sorts of astronomy in between. And what I'm most interested in is using it to do studies in our solar system to complement the spacecraft mission that we can send there with rockets like the SLS. But we can't send rockets everywhere because there's just too many objects in our solar system. So the James Webb Space Telescope will be complementary to that. And I'm going to say one more thing about Webb. If you could go to slide 33, please, because we have been making remarkable progress with the Webb Space Telescope. I'm sure you all know that it was launched and it deployed like clockwork on schedule. We are now in the process of focusing all the mirrors on the Webb to work together. So these are some images that were released from Hubble, released from NASA about a week ago, showing you that we are able to focus the individual mirrors and then in the bottom right, stack the images to make a single star image with our 18 separate mirrors. As of this release, those mirrors, although the images are piled on top of one another, they are not fully focused and phased working together. And so what has been happening during the past week and will continue to happen is that we will be phasing these mirrors so they work as one giant mirror that will have exquisite resolution in the near infrared and far infrared. So I'm going to stop talking there because I could go on for several hours, and I know that we have many other topics to discuss.
Well, I'm super excited about James Webb. I think it's going to be a great observatory, and I can't wait to see what you all are going to unlock. So, Kimberly, we just launched James Webb. We've got another big launch coming up, as Frank mentioned, a couple months from now, and it's going to have some secondary payloads, some smaller science and technology missions, and I don't think everybody hears about that. They know about the Orion spacecraft that it's launching, but they don't hear about sort of those other spacecraft that are launching with it. So I just want to see if you could tell everybody about those other payloads and sort of what you're excited about, what they're going to do, and give everybody an introduction to those.
Yes, thank you, Mary. I'll be happy to. So now, as you know, I'm the CEO at the Space and Rocket Center, home of Space Camp. But before that, I was at NASA, and the second to the last job before I left NASA was I was the payload mission manager for the upcoming Artemis I mission. And so I was tasked with identifying the opportunities that we could, the science opportunities that we could perform on this very first flight. Normally you get a flight under your belt before you try to add in the payload capability, but we were fortunate enough to be able to accommodate 10 small, what we call CubeSats. So when I was there, we found those opportunities, married them with the vehicle, and we designed and integrated into the rocket a deployment system so that these rockets, these CubeSats could ride up on the rocket into deep space and then be ejected or deployed into deep space. So this first flight, as I said, will have 10 CubeSats. They're about the size of a large shoebox. Think of a boot box or something like that, a little bit bigger than that. They are small packages, but they have very big goals that they're trying to accomplish. Just to name a few of them, there is one called NeoScout. It will perform reconnaissance and close proximity imaging of a near-Earth asteroid, or NEA. And they're going to ride on solar winds. They're going to capture them using a very large solar cell. This solar cell is very interesting. I love sort of how the mirrors unfolded on James Webb. And likewise, we have a solar cell that will fit into the palm of your hand, but when deployed fully, it will be the length of a school bus on all sides. So it's a really wonderful technology. It's a very easy way to capture energy in space and be able to propel yourself. Another one that I'd like to bring up is Biosentinel. It will actually use yeast as a biosensor to evaluate the effects of radiation on DNA. And this is very important to exploring deep space with humans. We have to understand how the radiation environment will affect humans right down to the DNA level. Another one is Lunar Ice Cube. It's going to search for water and other volatiles that are locked on the lunar surface in ice and liquid and vapor states. And it's going to use an infrared spectrometer to find those and understand those. And of course, as everyone knows, harvesting water on the moon or eventually on Mars is crucial to our exploration to those planets. We simply can't take with humans all of the water and oxygen we're going to need. So being able to produce it in situ is going to help us propel us further into the solar system. One other quick mention, Japan will actually attempt to land a payload on the lunar surface. And these are just some of the incredible science missions that will be happening on the first Artemis I mission.
Oh, that's awesome. I actually didn't realize Japan was having a payload on there. So that's wonderful. So we talked a little bit about, we just launched James Webb, what we're launching next. So now let's go a little bit more to the future. And so, Ralph, I want to bring you into the conversation and sort of talk about, you know, if you could do sort of the big next audacious science mission, what would you want it to be?
Oh, the next big audacious thing that we've been actually doing some studies on at APL are a thing called interstellar probe. If you could go over to slide 3, I believe. And so the idea, if you go into the full screen on that, so the idea here is to really be able to go farther and faster than the Voyagers, and actually to get out using modern technology to get out into out beyond our astrosphere, which is the magnetic bubble that that we find ourselves in, and to get out into near interstellar space and to take a look and see what our home in the galaxy really looks like. And to be able to do this, you need to have a really big launch vehicle, and so one of the things that we're looking at is the SLS. It'll of course be being used on Artemis.
Awesome. All right. So personally, if I could design my next big audacious mission, I want a 20-meter telescope in space. So I don't know, Heidi, if you feel that same way as I do, but so if you could design your big audacious mission, what would it be? And it looks like Heidi might be muted. Can you unmute her, Jamil, please?
Okay, great, thanks. I was locked out for a minute. Yeah, I'm right with you, Mary. I absolutely would like to build a really super large telescope. And it's not just me. The astronomical community just completed what we call a decadal survey. And one of the top recommendations for NASA was to pursue a Great Observatories technology maturation and development program so that we could realize this idea of a great observatory. And one of the key drivers for this great observatory is the question of whether there is life elsewhere in the solar system. Yeah, that's the logo for Astro 2020. That was our decadal survey process. If you want to just pop up the next slide, number 32, and share that. What they identified as a key science goal for astrophysics in the coming decade and beyond is a mission to search for the biosignatures from a robust number of, say, 25 habitable zone planets. That's a lot of code language in there. A habitable zone planet, we're talking about an Earth-like planet around a sun-like star that's close enough that water could be liquid on its surface. And by biosignatures, we're talking about measuring the spectra from these objects so we can actually measure the chemical constituents of that planet's atmosphere. And to do that, you need a large space telescope that has the same wavelength capability of the Hubble Space Telescope. So ultraviolet, optical, and infrared. Webb will be awesome, and it will be able to characterize a handful of planets. By handful, I'm talking about just a few, and most of them are not around stars like our sun, which is a nice sort of medium-aged bright yellow star, but rather Webb will be super great at looking at planets around what we call M dwarf stars, cool red stars. We really need a different kind of telescope to pursue Earth-like planets around sun-like stars. And if you could go to slide 34, I think that's maybe 2 steps forward from where you are. Yeah, this gives you an idea of what I'm talking about when I say a large space telescope. You see Hubble, you see Webb in the gold, and what we're talking about below that is some much larger, maybe anywhere from 6.5 meters to 10 meters. I'll take 15 meters, I'll take 20 meters, whatever you can give me. But the challenge is, just like Webb, we'll likely have to fold this up to fit inside a spacecraft. So the little video that was running was an example from one of the studies that NASA did going into the decadal survey. And really, you know, we looked at a lot of options, the teams that did these studies, and the next time step shows you an example of the kinds of rockets that you need to launch a telescope of this capability. The next slide, number 35. We looked, I think some of the slide is missing, but that's okay. You can see what we've got here is a couple of different versions of the SLS with this telescope folded up. We've also been looking at the Starship options because, you know, a big launch is what we need. So this is a question we could answer, whether life is out there or not. Why do we need the big telescope? Can't you just do it with small telescopes? Well, you really can't. If you could hop backwards to slide 21, this kind of illustrates for you why astrophysicists want to build this large telescope. This slide gives you a sense of how many star systems are available to you, depending on the telescope diameter. So 4 to 6 meters, these are actual stars that are close enough to the sun for us to do characterization. And you can see that with a 4-meter telescope, you don't really get out far enough or deep enough to really have a statistically significant number. Once you get up to the 10, 6.5, 10, 12, 15 meter, you start to fill in this diagram and you'll really be able to answer this question. Do any of the planets of these systems have the potential to host life? That's what we're looking at here. It's amazing to me that this is a question, a science question that has dominated the thought of humanity for literally thousands of years. Is there life elsewhere in the cosmos? And we are now, with the heavy launch capability, able to imagine a system that can answer that question. That's, to me, just an amazing science on the level of the Copernican revolution. This would be of that scale in changing our understanding of life in the cosmos if we can find a planet that has the signatures of hinting that there is life there. And you know, to me, that's amazing. I just, that's why this was a top ranked outcome of our decadal survey, because that's what we're looking at. Oh, and by the way, this telescope that we use to answer that question will revolutionize the rest of astrophysics as well, you know, just by the way. So that's important too.
Very exciting. I'll take 15 meter, even though I was hoping for 20, I'll take 15, Heidi. So we'll see what we can get. So let's talk a little bit about launch vehicles and science. You know, what are the critical factors that you're going to look at when deciding on your launch vehicle to do your science? Is it the lift capability? Is it the fairing volume? Is it the speed? Is it something else? And so, Ralph, why don't we start with you?
There we go. Unmuted. Sure. Well, actually, it turns out it's all of the above. For interstellar probe in particular, the thing that we're looking for is speed. And basically what happens is we're looking at the kind of science that you can do. And if you go to slide 4, I think, actually, give you an idea of sort of what the baseline example payload looks like and the spacecraft looks like. One of the things that we've done is to go through, this has been a multi-year effort involving several hundred people actually in the science community, taking a look at if we could do the next thing past the Voyagers, what would we do? And in looking at the science, that feeds into a set of instruments, and those instruments give you a certain mass and a power that you need, and that gives you a certain size spacecraft that you need. And once that you roll all of that up, it tells you how big of a launch vehicle that you need in order to get the speed up. Because what we're trying to do is to get something about the size of Voyager up to a speed about twice as fast as Voyager is going, with something like 2 times the launch energy of New Horizons. And actually, if you could go over to slide 6, I believe, to give you a little bit of an idea of, oh, here we go. This will give you an idea of sort of what an example might be that we could do with this mission using the SLS. This is an SLS Block 2 cargo version. These are notionally going to be available by the end of the 2020s. It's the sort of thing that we'd be able to use to take cargo up to the moon for getting our logistics in place up there. Of course, the usual launch sequence out of the Cape. This is coming up on the staging of the solids, and those peel off after we've gotten up through, of course, most of the atmosphere. Going on up, switching over to the exploration upper stage, the second stage of the SLS, to take us on up into not going to the moon this time, but actually to go into a nominal 100 nautical mile altitude parking orbit. That would line us up for being able to inject toward Jupiter. As we come back around, we'd use the EUS engines again to boost us, and then go over to a Centaur upper stage, a third stage, and then to a Star 48 BV fourth stage, and then finally the separated spacecraft. This is dominated by a 5-meter diameter high gain antenna. This would be the biggest high gain antenna that had ever been launched in one single piece into space on a spacecraft. The spacecraft would be spin stabilized as we go on out. And it looks like it hung up. Might want to restart it. There we go. So we would be going from the Earth to the moon's orbit in about 6 hours. One of the fastest escapes from the Earth. Deploy a magnetometer boom. One of the things to be able to look at the electrons in interstellar space are having wire boom antennas. These are all about 50 meters long. 7-month trip to Jupiter, a gravity-assisted Jupiter, picking up even more speed, and then past Saturn and Uranus and Neptune and the orbit of Pluto, and on out to the termination shock of the solar wind in about 7 years, through the heliosheath, and then past the heliopause in 12 years, and then finally out into interstellar space, going farther and faster than anything else, and getting out to about 350 astronomical units in something like about 50 years for a long-term mission. So, and yeah, if you could do full screen on this, this gives you again sort of an idea of what this would all look like in the packaging. Be ready to launch by the 1st of January of 2030. There are launch opportunities that come up every 13 months. There's a nominal good one starting in about 2036. Next gen radioisotope thermoelectric generators and communications available up to about 1,000 AU. And one of the things that we would be doing on this is basically be passing over control of the spacecraft and the instruments and the science on about a 10-year cadence. So there would be several generations of scientists that would be involved with this. So, in other words, this is sort of be the next big thing that we would like to do in heliophysics. A very large group of us. Right now, this is one of the missions that's being debated in the Solar and Space Physics Decadal Survey, and we'll see where that they come up with on evaluating the idea for this study.
Thanks, Ralph. Kimberly, is there anything you want to add from your perspective, working in the launch vehicles and working with scientists on sort of trying to match their goals and what they want to accomplish? And were there times that there just wasn't, current vehicle matches, and so they wanted to talk to you about what they could do maybe with SLS or other large vehicles?
Yes, actually, and I just want to say I'm so excited sitting here listening to Dr. Ralph and Dr. Heidi talk about this, what I call audacious science missions. They're incredible missions that are going to change our knowledge of the universe. It's just, you know, spine tingling, if you would, to think about. And in order to do this, we must have a heavy lift launch capability. And I would like to go further and say that it must be guaranteed. We must have a guaranteed way that we know of that will be in existence into the future. And much like the Space Launch System, will continue to evolve to accommodate these missions. This is very important because I think that they would agree with me that when you go to design your payload, it takes years and years and millions of dollars to design these incredible payloads. And what they need to know as they do that is they need to know what the vehicle is that they're going to ride on. And they need to know things like interfaces. And as much as we can drive toward common interfaces across vehicle platforms, I think that that is very much in the right direction. However, these large vehicles have even more intricacies in the way that they're lofted, and their environmental factors like temperature and airflow, which are very important to the payloads as they're on their way to orbit, as well as G levels and vibrations. And they need to know this well ahead of time so that they can build the robustness into these payloads that they need. And so I would say that we need to make sure while we're going out and we want more companies to enter into the field to produce even more possibilities of launch capabilities and to drive costs down, I don't want us to lose sight that we need a government provided guaranteed vehicle that we know will be around for years to come so that our researchers can dream and build the payloads of the future.
Thanks, Kimberly. So Heidi, can you talk a little bit about your experience and probably with James Webb and other spacecraft of sort of, you know, what you've had to do to modify and change requirements sort of to be that are, and your cost and schedule that have really been driven by launch vehicle constraints and where you've had to redesign things because of the launch vehicle?
Yeah, sure. In the case of James Webb Space Telescope, the decision was made moderately early on to launch on an Ariane 5 rather than one of the US vehicles. And that was because we have a strong and robust collaboration on this program with ESA. And it was a good decision because they did a perfect job with the launch. They injected us in exactly the right orbit. So that was great. One of the constraints we face all the time, though, of course, was the fairing size. And we did have to fold James Webb up significantly to fit inside that. And also mass constraints. We spent a lot of discussion managing mass during the development phase. It was a very tight constraint. And, you know, and that drove decisions on materials, it drove decisions on design, it drove decisions even on how the fuel is managed inside of its tank on the spacecraft, thinking about that. So having capabilities that provide you with more mass capability, that gives you a little bit of freedom to have more flexibility in your design phases. Having the larger fairings, it loosens the constraints on how much you have to compress and fold this thing. I think, and I would have to double check this, but I think that the total clearance that we had inside the Ariane 5 fairing for James Webb Space Telescope was on the order of centimeters. So it was pretty tight fit, but it fit and it worked perfectly. So I'm happy with that. Another thing, you know, I wanted to mention too, Mary, not so much for the telescopes, but for the kinds of missions that Ralph was talking about, or the kinds of missions that we think about in the planetary science community, having the speed of this large vehicle really makes a huge difference. I mean, you see my friends back there, the planets Uranus and Neptune. These planets are virtually unexplored. We did fly the Voyager spacecraft past them back in the 1980s, and but there have been no missions since. And if the next planetary decadal survey says, you know, yea, verily, thou shalt go back to an ice giant, with an actual orbiter mission of the class that we've studied Jupiter with or studied Saturn with, these planets are really far away, and we need the speed of a large rocket like an SLS to get there in reasonable timescales, to be able to do direct trajectories to Neptune or to Uranus, rather than having to do, flybys, gravitational kicks from Jupiter. And so we didn't really talk much about the science of those planets today, but I can assure you that there is magnificent science to be done in those systems that will require the capabilities of an SLS class vehicle.
Yeah, that was actually my next question, Heidi, was are there missions that have been sort of impractical or impossible, but now maybe could be enabled by SLS? And it sounds like you just gave us some great planetary missions, but I'll ask the other panelists, are there some other missions that you know of that have sort of been impractical, impossible, that you now do have SLS?
Really, you want to talk?
Well, I think my video is frozen. Can you hear my voice?
Good. You're good.
Okay. All right. Well, and I'm sorry, your question, Mary, was what other missions could we possibly do?
Yeah, what else has maybe been impractical or impossible, but now, Heidi talked about the speed, just having that speed to go see Uranus and I forgot your other planet over there, Heidi.
Neptune.
Sorry.
Yeah.
Not sure that those really look like the planets, but yeah.
Well, so I think we talked about one, the LUVOIR, if I'm saying that correctly, Surveyor, which is the Large Ultraviolet Optical Infrared Telescope. And again, it's all about the size of the mirror that you can get. And that is just incredible and opens up the universe wider, and lets us see further. The other that I would mention is the Europa Lander. The Europa Clipper mission is the first mission, and it's scheduled to launch later this decade, and it's going to do flybys of the Jovian moon, Europa. And it's one of the places that we could find extraterrestrial life. They have a major ice shelf on Europa and plumes that are coming out of this ice shelf. And it's basically a water world. So the idea is that Europa Clipper will fly through these plumes or be able to gather information from these plumes and try to understand what's underneath the ice shelf. And then hopefully we will be able to create a Europa Lander mission where one day the Europa Lander will fly on SLS and be able to go down and collect samples as we continue to search for life. So to me, those are just two great missions that we know of that have been discussed and possibly on the horizon that we would really like to work toward as we just continue to open up and understand science around our own solar system.
Ralph, did you have anything else you wanted to add? Otherwise, I got another question for you.
Well, I'm going to jump back to Interstellar Probe again and just say that, simply put, that having a super heavy lift launch vehicle like the SLS is enabling for Interstellar Probe. Without that, we would be stuck at much slower speeds, and one has to worry about the lifetime of probes. I mentioned that for Interstellar Probe, we're looking at a 50-year lifetime. That's largely driven by the lifetime of the power supply. It's driven by radioisotope decay of plutonium-238. And so the question is, how far can you get in 50 years? Well, to get as far as you possibly can in interstellar space, you need the speed. And again, what we've done with this is crafted an idea where that there are actually a third and a fourth stage that are carried along with the spacecraft, a very capable spacecraft under that fairing. So you really need this next quantum leap in launch vehicle capabilities. And it turns out that the kind of capability you have with the super heavy lift launch vehicle class, like the SLS, which you need for getting people to the surface of the moon, is just the right Goldilocks spot for having the kind of vehicle that you need to carry an interstellar probe out coming up with in the next couple of decades. So we need this one, and we need something like this. And again, without it, we just couldn't do this kind of a mission to find out more about our space and the galaxy.
Mary, I want to add to something to try to make it a little visceral for people when we're talking about the need for the speed. When we're talking about the more conventional rockets that we've launched missions on in the past, let me use Voyager as an example. That mission was developed when I was in elementary school. It launched while I was in high school, but it took all the way through to the end of graduate school before it got to the planet that I ultimately studied with it. All right. And then, and so what happens is if you're trying to advance science and retain the workforce that you need, when your projects, if you're using rockets that take, 15, 20 years to get to your targets, you aren't able to maintain the workforce. It's not like Mars where you can, every 2 years you launch a rocket and then, it gets there in a year and it's all hunky dory. I mean, it's very different when you're talking about deep space, like the outer solar system, even the, Saturn system and beyond, and certainly ice giants and the kind of stuff that Ralph is talking about, interstellar work. This is where the speed makes a difference. It goes from a generation to actually, years that you can imagine working with. So I just wanted to make that point. We have a lot of patience for those of us who work in the outer solar system and in deep space. And of course, patience for these large telescopes that we were talking about as well. But this is where the speed factor coupled with the lift capability to get the big payloads up really makes a big difference.
Yeah,
well, I think that's, sorry, Kimberly.
Oh, I was going to add, Mary, I like to colloquially refer to this as the time machine effect. This is the closest thing we have, is the speed and high energy of a large launch vehicle that we have to actually creating that time machine of science fiction. And just getting there faster and peeling off those years till we can start getting that science is just tremendous to all of us in the field and all of those that study and do research, so that they can capture it in a reasonable amount of time frame and begin to analyze the data, make decisions, and then design the next vehicles. So I think what Heidi was talking about with the speed is just super important.
I think often,
go ahead.
sorry, Ralph.
Well, I was just
often I think we looked at cost, and we look only at this is what a spacecraft costs, this is what the launch vehicle costs, but we don't look at the whole picture of, it's going to cost more for these grad students, years of their lives that we could shorten and help them. And you could also have the return of the science. And so, Ralph, I'm hoping you maybe want to talk about sort of those costs, that goes into these missions a little bit. And, if you had like an SLS capability, how, maybe, are there missions that actually cost less when you look at the big picture because you have that SLS capability?
Well, again, you could think about doing things like interstellar probe and think about doing things like going out to a Neptune orbiter, such as Heidi was talking about, with things with less capability. But to do that, you'd have to put together multiple duplicates of much smaller vehicles. They'd have to be using multiple gravity assist. You'd add probably a good decade to the kind of flyout times that you would need, and all of that ends up adding to risk. You probably would end up with having some missteps and some failures. Heidi's already talked about the idea that with SLS, you can enable actually doing direct trajectories. And so this takes the risk down because it takes the time down. It makes things simpler. And, NASA has done a great job of making space travel look dead simple, but it's complicated. It's not like counting backwards from 10 and then pushing a button and having a launch. And, I was going to say the other thing that again, we sort of lose track of, and it's very hard to keep up with, is how long it takes to traverse these distances. And I always, Heidi, I think, had some good points. I keep coming back to the lines from A Hitchhiker's Guide to the Galaxy, that space is big, it's really big, And one of the things that's very hard for us to kind of get our heads wrapped around is the fact that it is so big, because it really is outside of the realm of most of our everyday experience. And again, having things like the SLS with that kind of a capability all of a sudden enables us to pass the threshold of doing new things and new science that otherwise it just wouldn't be doable. So, trying even to put a price tag on it is a difficult exercise at best, when that you go from actually being able to realize doing something that even with a mountain of money otherwise just would still be outside of your reach.
I realize we all have gotten a little bit excited over here, which is a good thing. But I do want to make sure everybody knows they can type in questions to the chat. If not, we're going to keep going because we're excited. I will say we did get a comment in the chat that somebody knows that Dr. Alan Stern has been talking about a Pluto orbiter that would get there in 3 to 4 years using SLS, and just sort of says, let's see what the planetary decadal says. So, Kimberly, I see you shaking your head. Heidi shaking her head. Ralph, I think I got a nod. Kimberly, is there something you wanted to say about that?
Well, go ahead.
Go.
Well, I was just going to say, so I know Alan very well. I mean, I was part of the Pluto underground, and I've got an experiment that's actually on board New Horizons right now. And we're looking, of course, we're past Pluto, but we're looking at getting out into the outer heliosphere with New Horizons. New Horizons had the fastest launch energy from the surface of the Earth, and what we're talking about with SLS is that you could double that. And so, right, that ends up pulling your time down. You could get out to Pluto that fast. Of course, you've got the interesting problem that if you want to go into orbit, you have to figure out how to put on the brakes. And that, as they say, is a different story. But nonetheless, having these super heavy lift launch vehicles with these kinds of capabilities for science, again, it opens a new window on the world and on the universe and on what we can do.
Yeah, and let me just add to that. One of the things that we're limited by is launch. If their SLS program was robust enough that we could even imagine doing not only a Pluto orbiter or a Neptune orbiter, but both of those things, that puts us in yet a completely new realm of science in terms of the comparative planetology we can do. Let me show you just one super quick example. Neptune has a very large moon called Triton, which is an amazing moon. It is cryogenically active. It has cryogenic volcanoes literally erupting. They were erupting during Voyager. And this moon is in a retrograde orbit. It goes backwards around the planet. It's in fact a captured Kuiper Belt object. And it is almost identical in size to Pluto, which is a natural in situ Kuiper Belt object. If you can imagine a set of missions that would send the same spacecraft to both of those worlds and study them in a comparative way, we would learn so much about the Kuiper Belt and the objects that are there, not only the local ones, but one that has been captured and perhaps transformed, and has an atmosphere and has cryovolcanoes, perhaps even has a subsurface ocean that is contributing to these active cryovolcanoes. I can't imagine doing that in a world that doesn't have an SLS capability. And it needs to be a robust capability, not just we'll do one this decade and 5 decades from now, we'll do another one. You need to be able to do them together. But I can dream. I dream about things like that. And so that's one reason I get excited about talking about these kinds of capabilities, because I, as a scientist, oh boy, Pluto, Neptune, extremely large space telescope to find life elsewhere, sending spacecraft out into interstellar space, all of these things that they sound like science fiction, but they can be enabled by science on SLS.
Yeah, and Mary, just a little bit more. I love what Heidi is talking about, especially about coupling, those missions together. And we have all been so intrigued with the planet that's closest to us, which is Mars. And we love the Mars rover, the Curiosity, and we love Ingenuity, the helicopter. And to think that if we could package those up in a heavy lift launch vehicle, we could deploy multiple all over the surface of Mars at one time. As far as they've gone is about 15 miles. But if we could stage them. And so the other thing that we worked on briefly, which I would love to see, was kind of a mothership that could fly on a heavy lift launch vehicle and could take some of the communication and other basic subsystems and put them on what I call a mothership, and then fly to the area and deploy multiple payloads, either to different targets or different surfaces or whatever, different areas, and then have a mothership that hovers around and brings all that communication back. I just think that there are so many things, like Heidi said, we can dream of one day of not only going further and faster and farther than we've ever been before, but multiplying the science of the places that we've been, because even with all that we're doing, we still only get snapshots. And the more pictures we get, the more information we can harvest, the smarter we're going to be.
All right, we're getting excited, and it looks like Heidi already answered one of the questions, so I'm going to keep going. And I feel bad because Kimberly spends every day with kids, and so we haven't really talked about her day job at the U.S. Space and Rocket Center, but because she spends so much time with all these kids in Huntsville, I want to know, what is exciting to kids? Is it the science? Is there particular science? Is it the human space flight? Is it a combination?
Yes, I absolutely think it's a combination. We have, we're the world's largest STEM camp. And so during the summer, we come through, we have more than 1,000 kids on campus every week that are coming in. We have an award-winning planetarium where we do live program, and we can fly you from where you're standing on this planet. We can fly you out to the absolute outer portions of the known universe. And it's an incredible journey to do that, to see all of that. And so I think that is inspiring to them. We talk about human exploration as well. And we let them go through the paces of what it's like to be an astronaut, to train like an astronaut. We have Mars habitats. We have rovers, if you would, where they can learn to try to operate robotics on another planet. We also have Aviation Challenge, where we talk about the challenges of aviation around our own planet that we still need to conquer. And so they are extremely excited. I will tell you, we have graduated more than a dozen folks that have gone on to become actual astronauts, some of them both in the commercial and in the NASA realm. And we have 3 more that were chosen as Artemis astronauts that could possibly be one of the next humans to walk on the lunar surface. So we're in the business of inspiration and using what we call the power and the passion of space exploration to show people what they can do with their lives, and how the work that they're doing, like the work of Heidi and Ralph, how that can transform our lives on Earth, how that can transform our knowledge of the universe and our place in it. And like I said, I think both of them are equally fascinating to our students. They're very bright folks that come here. And I'll tell you, even interesting to them, we put in a class or a session on space policy and what we're going to do when we get there. How we're, how do we make rules for interstellar travel? And even that is fascinating to students. So yeah, I think all of it is extremely inspirational to the students that we see.
All right. I know Ralph has a hard stop at 1, so if you do have a question, put it in before he leaves us. But so I want to ask all of you sort of, how do you envision sort of the future and deep space, human exploration, and the space sciences working together? So I'll start with you, Ralph.
Well, we need to keep going. I mean, when that you're looking at things that we do scientifically to try to push the ball further, you don't have the option of standing still. You can either keep going forward or you will fall backward. And we've done an amazing job, I think, of being able to reach out and learning more things about our environment out there, and that's been the scientific part. But the exploration part's there too, because this is all about being, overall being a human undertaking. And part of this, and actually, can you put up slide 7? Just to remind people of this one. Exploration is sort of it's a funny thing, because it really is a question of us reaching out and trying to get an idea of what's out there. And I don't know if you can see the quote by T.S. Eliot, but this has been used by Ed Stone a lot in talking about the Voyagers, about why that we explore, because part of that is learning about ourselves and learning about our home. And, it gets back to arriving where we started and knowing the place for the first time. And I think that that's what all of this is about. And even though when we talk about space, we're intuitively looking outward, there's a big part of it that's looking inward as well as we keep moving along.
Beautiful. All right, I'm going to move over to you, Heidi. Do you remember the question?
I do. The question, well, the way I heard the question is about the interplay between the science realm and the broader space exploration realm, the astronaut realm, the commercial realm. How do they interact with one another? I agree with Ralph that all of these things are important. They play together in important ways. They all have inspirational value, of course. They all have educational value. But let me just point to the Hubble Space Telescope as an example of a merger of the human spaceflight program and the science program, where each was equally important to the success of one another. It was the astronauts that launched that mission. It was the astronauts that serviced it 5 times, pulling out old instruments, putting in new instruments, keeping that telescope at, the very peak of its capability for over 30 years. That was a triumph for both human spaceflight and the science realm working together. And so in my imagination of the future, we launched Webb on a single rocket without humans deploying things, and I can imagine our next one that we talked about, where it is again just launched on a rocket and deployed. But I can imagine even further, where we may want to build telescopes that are so large that we can't even imagine launching them on a rocket, not even the SLS. But maybe we have to actually build them in outer space. We can send up tiles and assemble them in outer space to make a much larger telescope than we could ever do on the ground, because the ground, the gravity just kills us, right? So I can imagine a future where that space enterprise works hand in hand with the science enterprise. So you have both the human spaceflight and science working together. I can also, I'm a child of the era of science fiction of Isaac Asimov and Robert Heinlein. I read it all. And, I can imagine a future where we actually get those scientists back to the surface of Mars, or get the scientists back to the surface of the moon. The science would be, we do great work with our rovers, right? But our human brains are incredible processors. So having a human brain attached to the capabilities that we have on our landers be pretty darn amazing. So I envision a future where these things continue to work together. I would never say, oh, stop the science in favor of human exploration, or vice versa. I don't think that's the right path. The right path is, how do we work synergistically together?
Kimberly, I'll turn to you. Oh, she's muted. Jamil, do you mind trying to unmute her?
Okay, there I go. Yes, I underscore what's been said here. And there was a question in the chat about, is SLS talking to SMD? And I will say, yes, they are. But I want to please suggest that even more discussion needs to be happening, because as vehicles are built for human exploration, we need to ensure that they are able to accomplish science goals as well. And that needs to be happening early in the development and the evolution of these rockets, so that while usually humans are a fairly fragile payload, and so usually those human vehicles will work well for science, but sometimes these science instruments are so extremely sophisticated that you need even more controls or an even lighter touch than you do even with humans. And so those need to be built in up front, so that we are creating vehicles that will not only evolve over time, so that we don't have to go back and create a new one every single time we have a mission in mind, but they can evolve over time and they can be used for multiple purposes. You know, the development costs are what's so expensive with these vehicles. And so once they get developed, then we just need to look at optimizing them for the human payloads and then for these wonderful science payloads. And that's going to take a lot of communication and a lot of realizing the multiple use purposes of these heavy launch vehicles.
Mary, you're muted.
Sorry. I just want to say thank you so much for joining us. I know Ralph has to leave us, but it has been such a pleasure talking to all of you. I'm excited for the future. I think there's a lot of great science opportunities to come, and I'm excited by what SLS will enable. So I'm going to turn it over to Frank and let him close us out.
Yeah, thank you very much for speaking today, and thanks for those of you who joined in. This is one of a series of these we're doing. The next one we're going to have will be on March 25th, and it's going to feature some folks from Lockheed Martin talking about Orion, but most specifically talking about how you design a crewed spacecraft for basically deep space exploration. You know, we've had spacecraft for a long time going to low Earth orbit. We've got new ones coming into low Earth orbit, but the challenges of going beyond the Earth's magnetosphere are quite different, particularly on very long voyages of many weeks or even longer than that. And so they'll talk a little bit about what went into the design of the Orion and the kind of challenges they're facing with that. And I hope you'll join us. Thank you once again for being here today, and thanks to our speakers. Have a nice weekend.
Thank you.
Bye. Thank you.